Well, good day, students. And in today's class, we're going to speak about learning and memory. Now, let me remind you, as I've been doing throughout this course, that in physiological psychology, what we're doing is we're exploring many psychological concepts, and we're looking to see if there are underlying processes taking place in the brain that can explain these processes. And learning and memory is something that has undergone great amounts of research in the realm of psychology. But one of the most interesting things is also that within the past 50 years, we now understand a lot of the neurobiology that supports learning and memory. So learning and memory is a concept that would have once been very abstract and difficult to define. But we now know we're able to explain what exactly is going on in the brain to some extent when learning and memory takes place. We're going to explore that in today's lecture. So this is just a brief review of some of the learning objectives. We'll talk about different types of memory, and we'll talk about different parts of the central nervous system that are involved in learning and memory. In particular, we want to focus on a concept called synaptic plasticity, because the core of learning at a neurobiological level is this concept of synaptic plasticity. And then finally, we'll just talk a little bit about dementia, and particularly Alzheimer's disease, because many parts of the world have an aging population, and this condition is becoming more and more important within the socio-economic affairs of many nations. So let's just begin by some brief definitions. We can say that learning is a process by which an organism acquires knowledge about the environment. And we've heard many times before the whole issue of nature versus nurture. Are we primarily a product of our genes and our biology, or are we a product of our environment? And the answer probably lies somewhere in the middle. However, for the environment to have an impact upon us and to shape our behavior, we have to understand the environment. We have to acquire knowledge about the environment. And learning is a process by which that knowledge impacts upon our biology and changes our biology. So we can say then, learning is a process by which an organism acquires information or knowledge about its environment, whereas memory, very closely related to learning, would be how are those information processes stored? It's the storage of that knowledge. So learning is the process by which it is acquired, and inside of that is the term encoding, and memory is the process by which it is stored. But whenever you talk about storage, I'm sure many of you would have been doing an exam, and you come across a question and you know the answer, but it's difficult to recall the answer. We often use a phrase, it's on the tip of my tongue, or you just know it's there at the edge of your thinking. So what that tells us is, even though something is stored, it's very important that we also have a retrieval mechanism. So once it's stored, how do we read the information from our neurobiological systems? And that's an area under intense investigation as well. So we can say that these three facets of learning and memory can be described as acquisition, storage, and retrieval. Let me say that again. These three facets of learning and memory can be described as acquisition, storage, and retrieval. And you can see this diagram will then show you the process of information coming into the brain through the stimulus. It's encoded by sensory processes, and then it goes into your neurobiological systems or your central nervous system. And we're going to discuss what those systems are and try to answer two fundamental questions. The two questions that we'll be seeking to answer are, where in the brain are memories stored? And what are the mechanisms by which those memories are stored? Where in the brain are memories stored? And what are the mechanisms by which those memories are stored? Okay, so to help us do this, we're going to do learning from movies to help us engage in this process. So this is a very popular movie called 50 First Dates. And I just want us to look at the trailer. Many of you may have seen the movie, but if you haven't seen the movie, I'm hoping you can get a sense of what the movie is about by looking at this trailer. So let's begin.
Dr. Henry Roth's best relationships were with his patients, and he wasn't looking to settle down. But one day, the unthinkable happened.
Are you staring at me or her? Because you're starting to freak me out.
And Lucy.
Henry Roth.
The only problem is...
Good morning. What is going on?
About a year ago, Lucy was in a terrible car accident. She lost her short-term memory.
Poof! She won't remember him tomorrow.
Don't you remember me a little?
From Columbia Pictures.
Every day you get her to fall in love with you again? You don't even open the freaking car door for me anymore.
You're in trouble.
Comes a story about winning over the girl of your dreams.
Do you have any idea who I am?
I've never even met you.
Every single day.
Excuse me, Lucy Whitmore?
Yes?
I have a delivery for you.
I have a secret admirer.
Adam Sandler.
When she stops, just let her pet you and look cute. Okay, here she comes. Smile. Why is she not slowing down? Uh-oh. Oh, no! That didn't work.
Drew Barrymore.
Pretend you're attacking me so she pulls over.
What do you think you're doing? Coming over here, taking our pineapple.
Help me, please.
I'm taking your big ass. Oh! Oh! Go! Ah! Oh!
Enough.
Are you okay?
Yes,
Okay,
yes.
I'll be right back. Hey,
Said
come
no,
here!
no.
50 first dates.
So that's the trailer for the movie 50 First Dates. And I think you could get from that trailer why we're considering that movie. Inside of that movie, the main character, played by Drew Barrymore, she has a learning deficit. And her learning deficit, or her memory deficit, is she cannot form new memories. As a result, even though she goes on a date with Adam Sandler and it all goes very well, the next day she doesn't remember Adam Sandler, she doesn't remember the date. And Adam Sandler is forced to start all over again in his pursuit of Drew Barrymore. Now, I'm not sure if the makers of this film actually were aware of the famous case of patient HM, but the film has many similarities to the famous case of HM. And I've told you before that we gleaned a lot of information about the neurobiology of different psychological processes from clinical cases. And patient HM represents one of the most famous clinical cases in the history of neuroscience and psychology. We now know that patient HM, his name is Henry Molaison, because Henry Molaison actually passed away a couple of years ago. Before that, in order to maintain anonymity, he was just referred to as HM. And as a young boy, he had a bicycle accident and he hit his head. And he developed intractable epilepsy. In the 1940s, when he had epilepsy, we had much less or many fewer drugs used to treat epilepsy. And over the years, his epilepsy got worse and worse until in his late teens, early 20s, he was suffering several seizures every day. And it was making his life unbearable. In an effort to help him, he went to see a surgeon called William Schofield. Now, Schofield was a young neurosurgeon at the time, and he was known for seeking to understand the brain and also being a little bit of a rogue, somebody who was willing to try things that others were not willing to try. And based on the symptoms of HM, he realized that the epileptic center, or the foci of the epileptic seizure, was probably within the temporal lobes. And he recommended that the medial temporal lobes of patient HM be removed. I guess at this point, HM hadn't much to lose, and he agreed to have the surgery. And this is a diagram that just shows you the area of the brain that would have been removed from patient HM. You can see it in a schematic on the left of the screen, and you can also see an MRI showing the areas of the brain that have been cauterized or removed during the surgery for HM. Now, the surgery was actually successful, and patient HM had no more epilepsy. But a few days later, they began to notice something. They began to realize that HM had an inability to recall events that occurred after the surgery. He began to behave just like Drew Barrymore did in that movie 50 First Dates. he could not form any new memories. He could not form any new memories. And of course, this has a major debilitating effect on any human being. Because as you saw in the movie, you would meet someone today, but by tomorrow you would forget about them. And that radically changed patient HM's life. And he had to develop systems of recording everything that happened to him in order just to survive. To help him in that process, he began working with a psychologist called Brenda Milner. And her work with patient HM was instrumental in helping us to understand some of the processes behind learning and memory. So some of the things we could say about HM were, well, despite the surgery, he was above or had normal intelligence. So there was no problem with his intelligence. And there was no problem with his short-term memory, or what we call his working memory. And this can be assessed by what we call the digit span test, where you simply ask someone to recall a string of numbers. And most people can get up to 5 to 7 numbers. However, he did have this striking inability to consciously recall events that occurred after the surgery. And we can say that patient HM has anterograde amnesia. And that is characterized by an intact short-term memory, preserved memory for remote events before the surgery, but an inability to form new long-term memories. That was patient HM's problem. He had an inability to form new long-term memories. Now let's return to the previous slide. Now on this previous slide, the fourth point here was very, very interesting. As Dr. Milner was working with HM, one day she asked him to perform what's called the mirror drawing task. And in this task, you have to draw a star, not by looking at it on a piece of paper and copying it, but by looking at it in its reflection in the mirror. And we know mirrors laterally invert things. And so when you try to do a drawing like that, it's very difficult at first. And you make a lot of errors as seen in this graph here. But as you keep practicing, the number of errors you make throughout the day and trials gets less and less. And if you come back the next day, you find you start off with some errors, but you quickly learn again. And by day 3, you've learned, or you have the ability to draw the star almost as good looking in the mirror as if you were just copying it from a piece of paper. Now, the interesting thing about HM was even though he could not remember any new events, he was actually able to learn to draw this star. And this suggests then that there were two different types of memory operating inside of HM. One type of memory was a memory for facts, but another type of memory was a memory for how to do things. And Brenda Milner, working with HM, was the first person to actually discover that we actually have two different types of memories inside of our brains. Now, today that seems very obvious, but that wasn't obvious 40 years ago. So HM showed a disassociation of what we now call explicit or declarative memories, but his implicit or non-declarative memory was intact. So let's just talk briefly about amnesia because we're discussing HM. And here's a funny cartoon. We have a lady at the amnesia clinic, and the doctor is remonstrating with her. He's saying, "You're not going to get better if you don't start taking these pills." But of course she replies, "I keep forgetting." Quite funny, because obviously she keeps forgetting because she's there at the amnesia clinic. So we can talk about different types of amnesia. And what we see here on the bottom is what patient HM experienced. He experienced anterograde amnesia. Anterograde amnesia. After a traumatic event, he was unable to form any new memories, but everything he learned or remembered before the event was still intact. And we contrast this with retrograde amnesia, where after the time of trauma, you're able to form new memories, but there's a period of time before the trauma where you cannot remember anything. And depending on the extent of the trauma, that period of time can extend from a few minutes to days and even years. And so let us understand the difference between retrograde amnesia and anterograde amnesia. And so we learned from HM you have two types of memories: declarative memories, things you know that you can tell others, and non-declarative memories, things you know that you can do by you can show by doing. Let me say that again. Declarative memories, these are things you know that you can tell others. And non-declarative memories or procedural memories, things you know that you can show by doing. So let's look at the characteristics of explicit memory. Well, it's knowledge about the environment, and therefore we usually refer it to being autobiographical or factual. It's knowledge about places, peoples, things. It's the kind of knowledge that you are attaining even as you listen to this lecture. It's the kind of knowledge that's tested during an examination, when you demonstrate your acquiring of that knowledge by statements of fact, by answering questions, by doing a multiple choice. This is in contrast to implicit memory, which is knowledge of how to do things, like perform motor skills, ride a bicycle, drive a manual car, play a musical instrument, draw the stars we saw in patient HM. In this case, you demonstrate your learning not by telling someone how to drive the car, but by actually driving a car. So for example, if you taught your child to ride a bike and you wanted to show a friend that your child can now ride the bike, you wouldn't call your child and ask them to tell your friend how to ride a bike. You'd call your friend and let your friend see your child riding the bike. So it's demonstrated by improved performance. Unlike explicit memory, which requires conscious recall, implicit memory actually doesn't require conscious recall. It's reflexive and doesn't seem to demand higher cognitive functions. We saw this with patient HM because he was able to draw the star and demonstrate learning. But if you asked him if he had ever done that task before, he would have told you no. He has no conscious recall of ever doing the task, but his learning is present, demonstrating he had been exposed to the task before. Implicit memory is acquired by repeating the same thing over and over again, and therefore it's acquired slowly. And sometimes you can actually take a declarative memory and by doing it over and over again, put it into implicit memory. So again, think of learning to drive a car. When you first start off, you're doing it in a very mechanical manner. But over time, as you take those declarative processes, you put them into action and they become implicit processes. Now, as we said, patient HM was the first person to allow us to understand these things. And this has now allowed us to divide memories into a complex schema. First of all, we divide memory into long-term memory and short-term memory. Short-term memory is also known as working memory. It only lasts a few seconds or minutes. When you look at long-term memory, it's divided into declarative and non-declarative, or explicit and implicit. And then even in declarative, you can divide it into memory for events, which we call episodic memory, and memory for facts, which we call semantic memory. An event would be what happened to you 3 years ago on your birthday. A fact would be a definition, like the definition of learning or the definition of memory. Under non-declarative memory, there are many different types. We talk about procedural memory, the acquisition of skills. We talk about perceptual memory, which has to do with priming. And then we talk about associative learning, like classical conditioning. This diagram is a diagram that just simplifies what we saw in the previous diagram and gives a couple more examples of how these processes take place. So what else did we learn from HM? Well, we began to get some clues or some insights in about some of the brain regions that are responsible for processing memory. And we realized the medial temporal lobes are very important. And what we've now discovered is that the hippocampus is crucial for memory processes. And what the hippocampus does is it doesn't actually store memory. Memories are not stored within the hippocampus. But the hippocampus seems to be vital for memory consolidation, the transfer of memory from short-term memory to long-term memory. And so in patient HM, both of his hippocampi were removed, and the result was that he could no longer transfer information from short-term memories to long-term memories. Now you remember in our study of emotions that the hippocampus was very closely related to the amygdala. And the amygdala is important in the processing of emotions. And now you can see that their close anatomical relationship is also noted by close connections between them. And you can see how emotions can have such a big impact upon memory, and how when something has an emotional content to it, it adds to the processes in the hippocampus and leads to enhanced long-term memory storage. So then, having said that the hippocampus seems to be important for converting memories from short-term memory to long-term memory, let's begin to explore, well, how are memories stored? And we're going to do that by looking at some examples of implicit memory. Now, one of the divisions of implicit memory is non-associative learning, and another is associative learning. And let's just look at a couple of examples of non-associative learning. One example that's very simple is called habituation. And the definition of habituation is it's a decrease in response to a benign stimulus that has lost its meaning or novelty. What do we mean is, well, in today's modern world, many of us have air-conditioned units. And depending on how old your air-conditioned unit is, it might make a lot of noise, it might make a little bit of noise. When you now walk into the room, if your unit is making a lot of noise, you notice the noise. That stimulus catches your attention. But over time, that stimulus no longer is registered within your brain. That's what we mean by habituation. You have an initial response, but over time you learn to ignore the response. Another example is a loud clock ticking in a room. When you now enter the room, you hear the clock and you hear the ticking or you hear the beeping. But over time you process that away and you no longer notice it. The key here is the stimulus is benign, it's not threatening, and so you no longer is relevant to you. Another example of non-associative learning is sensitization, which is an increase in response to an irritant or harmful stimulus. So in this case, there was a response and it wasn't triggering much. There was a stimulus and it wasn't triggering much of a response, but something happens and suddenly you have an exaggerated response to the same stimulus. Persons who suffer from post-traumatic stress disorder because they have gone to war might come home and they might hear a door bang and they might jump, they might startle because the door banging triggers in them a sense of a gunshot or the sounds of war, and they're highly alert to those things. That would be an example of sensitization. Now, the reason we've looked at these two examples is because there's been a great deal of work exploring these examples and these types of simple memory in the sea snail APLYSIA californica. And the reason we study this sea snail is because this sea snail has a very interesting nervous system. It's a simple nervous system, but some of the neurons are very large. And the person who pioneered a lot of the work on APLYSIA was Eric Kandel, who received a Nobel Prize for Medicine and Physiology in the year 2000. And he was the first person to be able to prove something called Hebb's postulate. Now, Hebb was a scientist from the 1950s. And in thinking about memories, Hebb made this statement, which we now call Hebb's rule. He said, when presynaptic cell A repeatedly takes part in firing postsynaptic cell B, the ability of A to excite B will be increased. Now that sounds a bit complex, but all Hebb was basically saying was if two neurons fire at the same time, something happens in the synapse that strengthens their connection. So the ability of synapse of neuron A to excite neuron B gets better. Today we put that in simple language. Neurons that fire together, wire together. Neurons that fire out of sync, lose their link. So we can take Hebb's postulate and we can just put it very simply. Neurons that fire together, wire together. And Kandel received his Nobel Prize because his work with APLYSIA was actually able to explain and provide the first evidence that Hebb's postulate was true and that something was happening in the synapses that caused memories to be stored. And we now call this synaptic plasticity, the ability of the synapses to change and hold that change over a long period of time. A plastic is something that you can shape, you can mold into a different shape, and that new shape will hold. And that's why we talk about the fact that synapses are not static entities, but they're dynamic entities. And when they change, they are able to store memories. So let's listen to a little short video about APLYSIA and the work done by Candel.
This sea snail, called APLYSIA, is somewhat of a celebrity, at least in the world of memory research. It was this lowly snail that revolutionized the way neurobiologists, like David Glanzman, think of memory. But how do you give a snail a memory?
We're going to give it a few shocks, but don't worry, it's not going to harm the animals. It's not going to produce any long-term damage.
Wow.
Giving it electrical shocks teaches the APLYSIA that the world is a dangerous place. How do we know it's actually learned?
We look at a reflex.
Touch the siphon of an APLYSIA and it triggers a defensive withdrawal reflex.
And I'm just going to touch the siphon like that. And there you see, that's the reflex.
This reflex can tell scientists if the snail has formed the memory.
The longer the gill and siphon remain retracted, that's an indication that it's learned what we taught it.
An APLYSIA that hasn't been given any shocks will respond with a short-lived contraction.
There it's out.
So what was that? 11 seconds. All right.
But an APLYSIA that was taught to be on guard responds much differently.
Now there's the reflex. Now the point is that it stays tucked.
So this guy's on a high state of alert here.
Yeah. So you see the siphon's just starting to come out now. And at 45 seconds. So it's 4 times as long as the naive animal. And it's learned that there's a danger in its environment. That's what it's learned.
This learning is observed in its changed behavior, but scientists can also see signs of memory in APLYSIA's legendary brain. Let's just say this sea snail is neurologically well endowed.
It has very large, huge, some of the biggest neurons in the world.
Its few but gigantic neurons inspired researchers to essentially create an APLYSIA mini-brain out of a sensory neuron and a motor neuron.
We take those out of the animal and we put them into cell culture and they grow together, and then we have a mini circuit, a neural circuit.
Scientists can see, on a cellular level, what happens as the mini-brain forms a memory. So, what is happening?
Basically, we see 2 things. The synapse between the sensory neuron and the motor neuron gets stronger.
When the snail gets zapped with electricity, the neurons start communicating differently, sending more, stronger chemical signals and receiving more signals. This change, which can happen quite quickly but doesn't last forever, corresponds to short-term memory. But administer the shocks over a longer period of time, and the 2 neurons physically change as the snail learns.
Anatomically, we actually see the growth of new synaptic connections between the sensory and motor neuron.
And it's this physical change in the neurons that is long-term memory. As the snail learns over time, its brain is making more and more connections, so that even when the snail gets a break from the shocks, it will still remember them. Besides training sea snails to be on a high state of alert, the research on APLYSIA has been integral in understanding learning and memory, and not just for snails.
When you're looking at these changes in APLYSIA, you're basically looking at the bedrock of learning. Those same processes take place in our brains.
And with the advancements in memory research that APLYSIA has already inspired, it is most likely going to remain in the spotlight for decades to come.
So let's just summarize a little bit of what you saw in that video. In APLYSIA, they have a gill, and the gill is very sensitive. If you were to touch the gill will be withdrawn in order to protect the gill. And we can use this process to measure learning and memory. If you touch the gill with a benign stimulus, what you find is the first time you touch it, it will withdraw and it will stay withdrawn for several seconds. But if you repeatedly touch it with a benign stimulus, you find the level of withdrawal gets less and less. And that's depicted in this diagram here. And that's habituation. If now you suddenly shock the tail, then you find the withdrawal response gets much larger. And that's an example of sensitization. Now, APLYSIA was important because what Candel was able to do was he was able to actually record from the neurons while these changes were taking place. And you can see here that for habituation, the stimulus neuron remained the same. That means the neuron that was detecting you touching the gill, the firing of the action potentials was exactly the same. But when you recorded from the postsynaptic neuron, what you discovered, the response got smaller and smaller. And Kandel was able to show that the reason the response got smaller and smaller was because of changes taking place in the synapse. Actually, less neurotransmitter was being released. He was also able to study sensitization and show that there were also changes taking place in the synapse that had to do with changes in second messenger systems like cyclic AMP and protein kinase A that led to more neurotransmitter being released. The exact details of which I don't need you to know for this class, but I do want you to appreciate that we have now been able to detail very clearly in habituation, in sensitization, the changes that are actually taking place in the channels and in the synapses due to potassium and calcium and all of these ions that we've been learning about actually changing. So it seems that these memories are being stored within the synapse. And we've been able to do that for classical conditioning as well. Now, I'm sure you've heard about classical conditioning. In classical conditioning, you present an animal with an unconditional stimulus. So in this case, the food is the unconditioned stimulus, and the unconditioned response is the dog salivates when it sees the response. Then you take a neutral stimulus, and if you ring the tuning fork, there's no response from the dog. But if you pair the tuning fork with the food repeatedly, what you find is over time, just the sound of the tuning fork induces salivation or induces a conditioned response in a dog. And what we've been able to show is that there are neuronal systems that exactly replicate classical conditioning. We've also been able to do the same thing for operant conditioning. In operant conditioning, a stimulus predicts a response, and it's used to change behavior modification in different situations. And again, I don't need you to know the exact mechanisms, but just for you to understand that by studying the sea snail and its nervous system, we've been able to explain all of these different types of learning and memory at a molecular or a synaptic level, giving proof to the whole concept of synaptic plasticity that Hebb would have first proposed. Now, the fact that it can happen in a snail, the next question is, well, does it happen in higher animals like mammals? And the answer to that is actually yes. We now know that there's something called long-term potentiation, which was first discovered in 1973. And in the realm of neuroscience, this is perhaps one of the most studied concepts. Two scientists working in Norway, Bliss and Lomo, were working on the rabbit hippocampus. Now, immediately when you hear hippocampus, you think memory. And they were able to discover that if you apply a high-frequency stimulus in the hippocampus, you change the response of the synapses. And that change in response can actually last for a very long period of time. And we call this now long-term potentiation. So LTP is defined as an enduring, long-lasting increase in synaptic efficacy following a high-frequency stimulation. Let's look at this example. If you just put some electrodes in the hippocampus, one to stimulate the nerves and one to record the nerves, and you stimulate every 30 seconds or so, you get a very nice stable baseline pattern. As long as the strength of the stimulus is the same, the strength of the response tends to be the same. But then if you suddenly give it what we call a tetanic stimulation, instead of stimulating every 30 seconds, in 1 second you give 100 stimuli. When you go back to stimulating every 30 seconds, the response is now greatly exaggerated. It goes from here to here, and you can plot it on this graph. And this exaggerated response actually lasts for more than an hour. In vivo situations, it can actually last for days. And this became the first evidence that you could actually get changes at a synaptic level inside of mammals. So the question people wanted to know immediately, well, does that mean that this is a form of memory? And while they were studying LTP, they discovered that one of the key receptors involved in LTP is the NMDA receptor of glutamate. Now, glutamate is the primary excitatory neurotransmitter in the brain. And glutamate has two types of receptors. It has ionotropic receptors and metabotropic receptors. The ionotropic receptors open ion channels. The metabotropic receptors are coupled to second messenger systems and G proteins. Inside of the group of ionotropic receptors, the two key receptors we want to focus on are the AMPA receptors and the NMDA receptors. Both are important for LTP. And if you block one of them, you can stop LTP. And so we have done studies, and when I say we, I mean scientists, where you can use a learning paradigm like the Morris water maze. In this paradigm, a rat is placed in a water bath. And the rat is obviously a little bit afraid and starts to swim around and eventually finds a submerged platform. And there it stops to rest. Now, if you put the rat in repeated trials, after a while it swims directly for the platform. There's some type of learning that's taking place. And you can see that by this red dots here, these red dots here. Over time, the rat learns better and better. Now, the rats that demonstrate that learning also have great LTP as seen by these red dots here. Now, if you give a drug that blocks NMDA receptors, you reduce the LTP significantly. The interesting thing is you also reduce the amount of learning taking place. And experiments like this now make us suspect and now make us think very, very strongly that LTP is a form of memory at a molecular level. There's other evidence, such like during the learning and memory process, you see LTP-like recordings in the hippocampus. And the hippocampus also has a rhythm called the theta rhythm, a pattern of firing, which is a very powerful stimuli for actually getting LTP in experimental situations. So taken together, we now think that LTP is a strong form of learning and memory. And LTP also has a friend called LTD, long-term depression. And this just means that synapses not only can get stronger, but they can also get weaker. And that makes sense, just like in habituation and sensitization. Some things you want to learn, some things you don't want to learn. And this duality gives your nervous system a lot more flexibility. Now, I want you to understand a little bit about how LTP comes about. And to do that, you have to understand a little bit about the NMDA receptor. Now, the NMDA receptor is a very complicated receptor, as can be seen in this diagram. But the most important thing that I want you to know about the NMDA receptor is it functions as what's called a coincidence detector. It detects when there's presynaptic activation and postsynaptic activation. When two synapses, when the presynaptic cell and the postsynaptic cell are functioning at the same time. How does it do that? Well, the key to understanding that is this magnesium ion here. Now, this magnesium ion sits in the middle of the channel and it stops sodium entering through the NMDA receptor and it stops calcium entering through the NMDA receptor. So when glutamate binds to the NMDA receptor, calcium and sodium cannot get in. But the magnesium blockade is removed by depolarization. So if the cell membrane depolarizes, the magnesium ion pops out and it allows calcium to enter the cell. The question is, well, how do we get depolarization in the cell? The answer is next to the NMDA receptors are lots of AMPA receptors. So when the presynaptic cell releases its glutamate, it binds to the AMPA receptors. And if a lot of AMPA receptors activate, the membrane depolarizes. When the membrane depolarizes, the magnesium ion pops out and calcium enters the cell. Now, once calcium enters the cell, it triggers a whole set of processes inside of the cell that lead to LTP occurring. You can read about these processes in your textbook. You have presynaptic processes and you have postsynaptic processes. The end result is the synapse becomes much more efficient and you get LTP being formed. And over time, not only does the synapse become much more efficient, But as you saw in the video, you actually form new synapses. There are new anatomical connections that are taking place. And we now know that these are also the result of LTP due to the activation of proteins and gene systems. And we've been also able to study LTD as well. And whereas LTP is the result of high stimulation, LTD is the result of low stimulation. And what happens is the amount of calcium entering the cell in each condition changes. And this leads to one or the other taking place. So low calcium leads to the activation of phosphatases and LTD. High calcium leads to the activation of kinases and LTP. And this diagram here just simply summarizes what we were saying. You don't need to know the details of these different processes, but I just want you to appreciate that we're studying these things and we're understanding them more and more as we go forward. So let's just conclude with some practical or some clinical correlations about learning and memory. These might be useful to you as a student. Let's talk a little bit about memory storage and retrieval. One of the things that happens is there's a tremendous amount of information coming at your brain every minute, every second. And your brain has to select and it has to choose what it wants to store. So we looked at the example of habituation. You enter a room, you hear a clock ticking, and your brain notices that, but does it need to store that information? Or after a while, does it just filter it out? The question then becomes, what allows the brain to make sense of particular pieces of information? And there are two things that we can talk about: reliability and importance. Reliability is, do we see that same thing happening over and over and over again? Does the same pathway keep getting activated? If that happens, that leads to the formation of the memory and new structural changes taking place. Now, for you as a student as studying, that tells you the value of repeatedly learning your work over and over and over again. There is value to repetition, even though it may be boring. The other thing that helps us store memories and retrieve them is the importance of the memory. Does it have an emotional attachment? Is it important to you for some reason? And if there's an emotional attachment, that means it tends to have more importance. So people remember arousing stories better than neutral stories. That's why it's important that you find some enjoyment from your studies, or you can attach your studies to an emotional experience somehow. All of these things are little tips that might help you with your learning. The other thing you have to think about is, once you've learned something, are there things that promote retention and are there things that remove retention? Well, sleep definitely promotes retention. We know that very, very well. Lack of sleep leads to loss of retention and storage of memories. Sleep after you study helps you to remember. That's why sometimes pulling the all-nighter is not the best idea. Another thing that we now disrupts memory is alcohol. Excessive alcohol consumption after studying probably will not benefit you. Dementia is a situation in which there's an underlying slow destruction of the nervous system. It's usually chronic and progressive in nature, and the result is there's a decreasing cognitive function. Now, as we all age, cognitive function slowly declines, but dementia sets in when that aging process goes beyond the normal aging process. And it can affect all aspects of cognition: thinking, comprehension, calculation, language, and judgment. It's a very debilitating disease, and it's very traumatic both for the person who's experiencing it and also the person who's taking care of the person who's experiencing it. And it's now reaching epidemic proportions in our society. The most typical form of dementia is Alzheimer's disease. But I just want to let you know that other things can cause dementia, like hypertension leading to repeated strokes, metabolic disorders, infections like HIV, and there are also some other neurodegenerative diseases. But the one that's receiving most attention is Alzheimer's disease, because we still don't know exactly what's happening in Alzheimer's disease. We do know in Alzheimer's disease there's a gradual loss of memory, and that it seems to affect almost half of persons who reach the age of 85. This is a PET scan just showing the activity of two brains, one with Alzheimer's, one without Alzheimer's. And you can see that there's markedly diminished activity in the patient suffering from Alzheimer's. The neurons of the brain just don't seem to be working as well. And when you actually look inside of the brain, you see that the neurons are undergoing a progressive degeneration. And it seems to be associated with the accumulation of something called amyloid protein. This is an abnormal form of a protein that's usually produced by the brain but processed by the brain. But over time, the accumulation of this abnormal form leads to the accumulation of plaques and tangles, extracellular and intracellular deposits that seem to destroy the cells of the brain and stop them functioning. Even this is still being investigated, and at this point we don't have a way of really treating and stopping the accumulation of these plaques and tangles. And so unfortunately there's no cure for Alzheimer's disease at the present time. Some of the drugs that we do use and have some effect at slowing the progress of the disease are acetylcholinesterase inhibitors. Acetylcholinesterase breaks down acetylcholine. So an acetylcholinesterase inhibitor stops the breakdown of acetylcholine and therefore promotes the amount of acetylcholine in the brain. And that seems to slow the progress of Alzheimer's disease. There are also investigations of NMDA receptors antagonists and seeing if these are working in Alzheimer's disease. These drugs, unfortunately, are not cures and only seem to allow memory to last a little bit longer. So that's it for learning and memory. I hope you've been able to understand that today we know a huge amount of learning and memory. It would have started with patient HM and all the things I would have learned from him, right down to modern day neuroscience, where we can actually get into the synapse of cells and the receptors and look at the changes in receptors of learning and memory is taking place. However, despite our huge advances in learning and memory, there's still a lot more to discover. And of course, as we've spoken about in this course, one of the things people are always pushing are for cognitive enhancers, drugs that can help us improve our memories and improve our learning. But of course, that's a topic for another time. So until our next lecture, you have a good day.